Okay, well, welcome everyone. Welcome to the Science Gateway. Welcome to CERN. For some of you, I'm sure it's the first time you've been here. For others, welcome back. This is the third time that we'll be doing Vox Days at CERN. We started back in 2017. We did another one in 2019. Then we had a little pandemic gap, and this is the reboot. And the idea is we'll keep doing this now for every couple of years. So welcome to this new venue, brand new Science Gateway. In this presentation, I'm Derek Mathieson. I'm an engineer at CERN working in a business computing group, and together with Sofia, who's part of the Quantum Technology Initiative. She's a coordinator and working in the IT department. We're going to tell you a little bit about CERN. As an organization, of course, it's very well known as a particle physics organization. In fact, we are the largest particle physics research organization in the world. But perhaps what you don't know is some of the things that goes behind the physics, what goes on behind the scenes in order to allow these discoveries that you've seen announced in various newspapers and bulletins around the world. So what actually goes behind this? What is CERN all about from an engineering perspective? As you know, we are an organization that studies does fundamental research on subatomic particles in order to have a better understanding of the universe. Our mission has four main pillars. So through research, we try to understand how the universe works. So I get an idea of what was the universe like right after the Big Bang, just when everything was beginning. To do that, of course, we need to develop new technologies for particle accelerators, new technologies for the detectors, and all of the infrastructure that we build in order to support this research. And by doing that, we also have to train the scientists and engineers of tomorrow. And in this environment, when they're developing these new technologies and pushing the forefronts of technology, we bring people together from all over the world. CERN is an international collaboration with people from all over the world working together with a mandate to build new technologies, make discoveries, and share that information with the rest of the world. CERN is a particle physics research laboratory, but that doesn't really give you the whole story. You've probably seen the headlines of these new discoveries that we've made, but what actually goes on at CERN? And while I'll touch upon the research we do at CERN, I wanted to tell you a little bit more about the amazing place and perhaps tell you a few things that you didn't know that go on at CERN. Most of the people working at CERN are actually here to design, build, and support the infrastructure that allows particle physics to take place. Be it the mechanical engineers that design and fabricate specialist equipment to the different components of our particle accelerators, to, for example, the civil engineers who build cathedral-sized structures 100 meters underground in order to house the particle detectors and this huge infrastructure, the largest scientific instrument in the world, which is actually literally under your feet. To the electrical engineers that design and build unique components to make the world's largest scientific instrument. This is an 18-volt power supply, so a bit less than a typical laptop charger, and it's actually used to power the magnets inside the LHC. It's 18 volts, but it has a capacity of 20,000 amps. I love these little stickers on it to say which is the plus and the minus on these 20,000 amp bus bars. So this is the kind of technology that we're developing. The extremes. This is the kind of technology where you don't find in the rest of the world. Computer systems and data engineers, of course, that build these systems to be able to manage and process this data, petabytes of information coming from the detectors, which need to be managed, stored, and processed. We've, of course, got many, many software engineers working at CERN who develop the software to run, maintain, support, and control all of these different systems that are operating at CERN. Beyond the engineers, we even have our own fire brigade, specialists, of course, in underground work, working in cryogenic areas, and, of course, radiation-controlled areas as well. Our medical service looks after our occupational health. And in fact, there's even some people who live at CERN. We have our own hotel with around 450 rooms, and so there are people who have literally lived at CERN for short periods of time doing research in this amazing place. It's a place of contrasts. From the mundane to the highly complex, this is a place of extremes. Massive civil engineering projects which have these cathedral-sized structures underground, literally under your feet today, studying subatomic particles, making discoveries at the subatomic scale. It all takes place here. CERN's internal distribution system moves around 180,000 parcels around the site every single year, from pieces of paper to parts of the accelerator complex. And because we're a transborder organization, our logistics system has to prepare around 80 different customs forms just to be able to move these items around the site. We have our own high voltage installation for power conversion, runs at around 400 kilovolts with a capacity of 200 megawatts. We're one of the few places in the world that operates its own infrastructure at this level. And as a transborder organization, and I say literally transborder in the sense that this red line actually shows the international border cutting across the CERN site, we have unique challenges, even for things like the guy who cuts the grass at CERN has to worry about the rules related to the international transport of waste as he moves the grass clippings around the site. Formed after the Second World War, CERN was one of Europe's first joint ventures. It brings together people and scientists and engineers from across the world to work together and then share openly all of the results that we produce with the rest of the world. There's someone from almost every continent of the world working somewhere on CERN. And in fact, it was because of this large and diverse community that CERN scientists Robert Cailliau and Tim Berners-Lee invented the World Wide Web. It's hard to imagine. This slide somewhat dates me. I started CERN in 1989. Just as the web was being developed, in fact. A friend of mine, Nicola Pello, was working with Tim Berners-Lee on one of her student projects, and I was helping her. Over lunch, we were chatting. And what we were actually working on was the world's second web browser, the line mode browser. A line mode browser was developed at a time when most people accessed to computers using terminals. And so you didn't have things like blue text with underlines to navigate to hyperlinks, and instead you actually just typed in the number at the bottom of the screen of the link that you wanted to jump to. And CERN has been at the forefront of technologies, everything from cancer therapy using compact particle accelerators to medical imaging using technologies that were developed at CERN as part of the particle detectors. Even to high-precision welding, there are 40,000 leak-tight joints that were made inside the LHC. And to do that, we had to develop new techniques in order to do specialist welding for these cryogenic leak-tight vacuum joints. This picture is from 1975, in one of our operator consoles of the Super Proton Synchrotron. And under his right hand is an early trackball. Basically, it's an upside-down mouse. But here is something much more interesting. This is a capacitive touchscreen. It was invented in 1972 by CERN engineer Bernd Stumm, and is now an integral part of every mobile phone. So, although CERN is very proud of all of these different innovations, CERN's principal role is not applied research, the kind of highly directed research that you would get within industry that can drive great innovation. However, you can't make the leaps of understanding that you can without fundamental research. And our goal is much more complex than that. To paraphrase CERN's Director General, no amount of applied research in a candle would lead to the development of a light bulb or an LED.
I think I can take over exactly to try and explain to you a little bit more, or show you exactly what Derek is meaning with this, and the Director General was meaning with this sentence. So those are pictures from cover of magazines that are fairly recent, 2021, Physics World, 2023, I believe the time. And they talk about quantum revolutions, they talk about quantum leap, but all of that started from fundamental research at the beginning of the past century. So we're talking about something, quantum mechanics, that physicists started to develop more than 100 years ago, okay? There is no more fundamental research than that, I would say, as a physicist today. Now, that was the seed to what we are trying to achieve today in terms of very, very advanced, exciting, and ambitious technology. Now, I forgot to say a very, very important thing I should say before I start my talk today. We do not have a quantum computer at CERN. I'm sorry about that. I know you signed up for the visits because you were expecting to see a quantum computer here. It's not the case. We are not building a quantum computer, for the moment at least. What we want to do first is to understand how we can use this technology for physics. Derek showed to you that we have a lot of things and interesting development and technology that we have here at CERN. All of those are targeted to our experiments, to learn better, to answer fundamental questions about the world. So also in the case of quantum technologies, this is the overarching goal. Can we use quantum technologies in whatever form to improve our physics science? And if in doing so, we need to develop quantum computers, maybe we'll do it at some point. But we are not at the stage yet. Okay, so just the little bit of introduction that I forgot to make because I wanted to jump right into quantum mechanics. Now, from now on, we can talk about quantum mechanics. I'm joking. So we talk about revolutions today, but those are not the first revolution. People that like to study the story of quantum technologies, they actually identify two major steps that happened starting from the beginning of quantum mechanics, so the beginning of the 20th century. The first quantum revolution was really the time in which, after an initial struggle in trying to understand how quantum mechanics work and how it compares to what classical physicists at that time knew about reality, that led to the first improvement in technology. Okay, so we can look at that as more than 100 years old revolution. Then by the end of the 20th century, we talk about second revolution. There, it's when we start to really be able to build artificial quantum states that we can use for our technologies. So let me explain to you what I mean exactly with these two very cryptic definitions. So, first quantum revolution, beginning of the 20th century, 1900, so was exactly the year the Max Planck published its paper on blackbody radiation. We don't talk about that, don't worry. But that was the seed to really point us toward concepts of quantization of energy, quantization of light, the duality between particles and waves, the explanation of the photoelectric effect, which was given by Einstein, was published by Einstein just a few years later and led to his Nobel Prize, by the way. The Nobel Prize to Einstein was due to his studies on quantum mechanics, not really on the theory of relativities, as everybody would think. So that's what's considered the beginning of quantum mechanics. The problem with quantum mechanics is that at the time, those new concepts that were needed to understand and explain the new phenomena were very far away from what physicists knew. One of the main problems was related to what's called entanglement. I don't know if you heard about that. How many of you heard about what entanglement is? Okay. How many of you can explain to me what that is? I see some hands. So if you'd like to give it a try. Yeah, exactly. I know. So they are correlated with each other. That's how you could translate entangled with each other. That's exactly true. Now, if you bring this to the extreme, this means that, in principle, the state of a particle knowing the state of a particle in a point in space will tell you something about the state of the other particle in another point of state, even if those two are separated by a distance such that no light, nothing, no bit of information could travel from one to the other. Now you can understand how this was very hard to frame within classical physics at the beginning of the 20th century. Because of the reasons there was a lot of debate where even paradoxes that were discussed by very, very important physicists at the time. So, but there was a long struggle before quantum mechanics actually became an accepted theory. In the meantime, all of these original observations and findings could be used to build new technologies. Everything that has to do with time clocks, transistors, lasers, this kind of technology was born after this first jumps into quantum mechanics had happened. Okay, that's why we call it first quantum revolution. Some theory that was still being developed was nevertheless at the seed of brand new technology. Then we can move forward to about the end of the century, and that's why I want to stress this time that the second quantum revolution is because at CERN we like to consider that we really had a strong impact on. And the reason being is that one of the most important works that actually led to the second quantum revolution was the work by John Bell, who used to work at CERN. John Bell, I talked about the struggle of understanding and explaining how entanglement works, whether it really creates a problem in the definition, in the description of the reality by quantum mechanics. Well, John Bell work is really the beginning of understanding how this is happening. And in fact, John Bell proved that no classical theory, basically in whatever form, can be used to explain the observations related to entanglement and quantum mechanics. He gave a mathematical proof that that is not possible. So you need quantum mechanics to explain the reality. This is the importance of his work. And from his work, over the years, from 1960s on, a lot of different experiments were designed in order to prove whether it was right or wrong, and those were all based on technologies related to lasers and optics. Indeed, I don't know if you know that in 2022, the Physics Nobel Prize was awarded to experimental physicists that had actually designed and carried on those experiments through the years. Okay, so this just gives you an idea of how important John Bell's work was. Now, in practical terms, what does it mean? It means that you can actually rely safely on entanglement as a way of relaying information. You can actually use quantum systems of entangled states. You can manipulate them. And that's why, and the manipulate part is really the part that signs the second quantum revolution. It's the step for which we are able to build artificial quantum states, configure them to our needs, use them to manipulate information. Okay, so that's why the beginning of that part of the century is really considered critical. So today, based on that, we are quite a few years beyond. There are a lot of different applications that are all based on these initial findings. Applications in communications, and I was briefly discussing at coffee about some of them. We can talk more about them. Applications in cryptography, applications in computing, applications in sensing. At CERN, we are particularly interested in what sensing means. It's the idea of using a quantum state and monitoring how it changes in order to find some information about some interaction that happens. For example, a particle that went through. You can imagine how this could have a direct applications in our detectors. So there are a lot of possibilities and a lot of interesting things we could do with quantum technology, and therefore, a few years ago, and exactly in September 2020, CERN has approved and started its Quantum Technology Initiative. And the idea, as I said at the beginning, is really to understand which aspects of those technologies we could use for our community. This is not something that CERN is doing by itself. You probably know and read the news about all the different research programs that are being developed in the different countries. So CERN is very proud to also be interacting with all of those countries and all of those research programs, and also to try to build a coherent, let's say, or a collaborative, as much as possible, effort. And so the Quantum Technology Initiative, in its first 3 years, has really explored a wide range of possible applications. Okay, and later on, I think I will be able to show you a few of those examples. But in the meantime, I'll let Derek continue.
Thank you. So yes, going back, our fundamental business is fundamental part of physics research, finding out how the universe works and understanding the basic laws of nature. Looking at our universe from the outside, current theories can account for around 5% of the universe. The rest seems to be tangled up in dark energy and dark matter. And the best way to understand how the universe better is to look back in time, back to when it all began. Cosmologists and astrophysicists have made great strides in this area. By looking back in time using telescopes and satellites, we can look back, but there is a limit how far you can go back in time, around 400,000 years after the Big Bang, before which the universe was simply too hot and light couldn't escape. But there is another way. By recreating the conditions that existed moments after the Big Bang, you can actually study the situation and understand better about what's going on in the universe. And to do that, you need particle accelerators. And CERN has the largest and most powerful particle accelerators in the world. And we can get back to the beginning of time closer than anyone else, to a millionth of a second. And we do that, as I say, using particle accelerators. In fact, most of CERN's experiments are related to bashing things together. It's like the kind of thing you had when you were a small boy, bashing train sets together to see what would happen. Well, we do the same, but at a much larger scale. So I'd like to explain a little bit about what a particle accelerator is all about. And to do that, I'd like to have a little game, which I like to call Angry Apples. So we've got two particles, in this case, two apples, and we're going to bash them together and to see what happens. So we'll bring in our particle accelerator, and we're going to charge up the particle accelerator, launch them off, and see what happens with this collision. Right, not very much. I think we would all agree that this is a low-energy collision. So, of course, if we want something more interesting to happen, we're going to have to beef up the energy a little bit and maybe introduce a more powerful particle accelerator. So let's bring in our next level up particle accelerator. And we'll see what we can do with this. Are we ready? Okay. We've done some damage. The particles have collided and changed direction. But nothing terribly unusual has happened, and certainly nothing that you couldn't describe with high school physics. Isaac Newton probably could have described this pretty well back in those days. So again, we need to increase the energy levels before anything really interesting starts to happen. So let's have a couple of particle cannons. This is bound to have something more interesting now, I think. Let's go. All right. We did have apples. We don't have apples anymore. But nothing really unusual has happened. Yeah, this is still into the realm of everyday life. Ideally, not too often do you see this happening, but we're still into normal everyday physics. But that's not what happens at CERN. When you go to incredibly high energies, when you get the particles traveling close to the speed of light, something quite different happens. So let's bring on the superconducting Large Apple Collider and see what we can do to put incredibly high energies into these two particles and see what happens. So we'll just have to fire up the accelerator. Whoa! So we started off with apples, and we've ended up with something else completely different. How can that happen? Wow! We even ended up with a cubeberry. These are incredibly rare. Oh, hang on. Go back. My animation didn't work there. There we go. It's just disintegrated into 3 blueberries. So what happened here? When we started off with 2 apples and ended up with the content of a fruit bowl, how can you transform matter into something else? Well, in fact, this is just an application of probably the most well-known physics formula in the world. E equals mc squared. And this formula explains that there is an equivalency between energy and matter. It's got c in there, which is a really big number. C, of course, is the speed of light, and squared is an even bigger number. What it tells you is you need an incredibly large amount of energy, but you can equate energy and matter. And that's exactly what's happening, in fact, inside the LHC, inside the particle accelerator. We take 2 particles, give them an incredibly high amount of energy, and as they collide, these energy allows you to create new states and new forms of matter. Of course, it's impractical to accelerate apples. So at CERN, we accelerate tiny subatomic particles, typically protons, around the accelerator and bash them together at incredibly high energies in order to create these new forms of matter. So how does that work? Well, it starts off with a bottle of hydrogen. As many of you may know, hydrogen is basically a proton with an electron spinning round about it. So the first thing we need to do is get rid of the electron. And we do that using a device called a duoplasmatron, which is basically a strong electric field that rips off the electron, leaving the protons to travel forward into our first particle accelerator. Our first particle accelerator is a linear accelerator. It's basically a 45-meter long tube, and inside there are charge plates which basically, with the electric field, will alternately push and pull the protons as they accelerate along the length of the linear accelerator. Within 45 meters, they're already traveling at 1/3 of the speed of light, 100,000 kilometers a second. Obviously, continuing to go in a straight line would be impractical, so the first thing we do is we gather them together in the booster, which is a small accelerator ring which actually gathers the particles into bunches. And once they're gathered into bunches, we then transfer them into our proton synchrotron. The proton synchrotron is our oldest accelerator, built in 1956. And within 1.2 seconds, this accelerator can accelerate the particles up to 99% of the speed of light. But it's an old machine, can't go any faster than that. So we then transfer these protons into the next largest particle accelerator we have, the super proton synchrotron. Cool name. The super proton synchrotron will then gather the particles together and accelerate them over a period of around 3 seconds. They are traveling at 99.998% of the speed of light. But again, this is an old machine built in 1976, can't go any faster. So we then transfer them into the Large Hadron Collider, 27 kilometers long. It takes around 20 minutes for us to accelerate the protons up to 99.9999991% of the speed of light, at which point they have an energy of 7 tera electron volts, an enormous amount of energy. So what happens then? Well, inside the tunnel, this is what it looks like. There's around 4,600 magnets in a long string that goes around the 27 kilometers. There's these blue ones, these are called dipole magnets. There's about 1,200 of these inside the tunnel. They run at cryogenic temperatures. They have superconducting cables carrying around 12,000 amps to create a magnetic field of about 8.3 Tesla. That's about 200,000 times that of the Earth's magnetic field. Inside these dipoles, you can see there are 2 small channels. This is where the protons live, flying around, going around the 27 kilometers, 11,000 times a second. The magnets themselves have to be built incredibly strong. This huge magnetic field of 8.3 Tesla actually exerts a force on the magnet itself of around 400 tons per meter. That's about the weight of a 747. To do that, the magnets themselves are actually assembled out of laminations of steel, special austenitic steel. There's about 6 million of these laminations inside the LHC. The whole thing itself operates at cryogenic temperatures of around minus 271 degrees Celsius. To make sure that the particles don't hit anything when they're going around inside the tunnel, we also have a very high vacuum, around 10 to the minus 13 atmospheres. It's about the same pressure as you would find on the surface of the moon. And the whole thing is running at cryogenic temperatures. The cables themselves are superconducting. These are traditional cold superconductors, nothing like LK99 or anything yet. So we're basically running at typical niobium tin. These are traditional superconductors. Modern high-temperature superconductors typically can't support the high magnetic field that we need in order to run these, to be able to bend the protons around this 27-kilometer ring. The whole mass of the LHC was around 31,000 tons of equipment. And to cool it down to cryogenic temperatures, we evaporated around 12 million liters of liquid nitrogen to get it down to cryogenic temperatures. The machine itself then operates it with around 120 tons of liquid helium in order to keep it at cryogenic temperatures. I think we're probably the only place I'm aware of that measures helium by the ton. The whole machine is underground, under your feet as we speak, housed in a 27-kilometer long tunnel. These large installations that you can see flying here, these are the various detectors, the various structures which hold the detectors inside the tunnel. And to give you a sense of scale, at the very top of the picture, you can see Geneva Airport. We're actually seated at more or less beside the Atlas detector, and you can see this huge infrastructure, the largest scientific instrument in the world, where we basically have the LHC and where the detectors and the accelerator actually lives. Inside the accelerator, the beams themselves are arranged in bunches. There's around about 100 billion protons in every bunch. And there's about 3,000 bunches themselves actually in each of the different tracks going around in opposite directions. The bunches pass each other about 40 million times a second. And as they get close to the detectors, we squeeze the particles into small bunches a few centimeters long and about 1/3 the diameter of a human hair. Once they approach the detector themselves, the two beams are brought into collision, and then the detector, which is effectively a large 3D camera, measures the tracks and trajectories of the various forms of matter that are created at the collision points. Every single time the bunch crosses each other, there's around 20 head-on collisions. These are the interesting ones. A lot of the other collisions actually are just not that interesting, so we want to throw away that data. This is a picture of a real detector. In fact, this is a picture of Atlas. This is the one which is more or less below our feet just now. Just to give you a sense of scale, down at the bottom you can see a person. These are cathedral-size installations built 150 meters underground. Together with CMS, that's Atlas, Alice and LHCb. These are the four main main detectors that you can find in the LHC. Atlas and CMS were the two detectors, or general-purpose detectors, which announced the discovery of the Higgs boson back in 2012. All of these detectors generate huge amounts of data, around 2 petabytes a second. It's impossible to store that amount of data, so we need to have some way of filtering it. And in fact, typically we only care about 1 collision in a million of data that we actually want to keep. The rest of it we want to throw away. So we have to have some clever way of filtering out all of this data. And we do it with a multi-level triggering system. There's 3 levels. The first level trigger is typically done with specialist hardware. And then second level trigger is typically done with a local compute farm, and then finally there's a large data center that does the final processing and elimination of the unnecessary data, which are then the final data is then shipped and stored locally at CERN. Interestingly, one of the detectors has taken a novel approach to doing the first level trigger. LHCb has decided to use a GPU farm to do a full software trigger. So they take the 32 terabits a second of data coming from LHCb and process it in a compute farm locally using GPUs. Around 160 server-grade GPUs are then put together to filter the data from 32 terabits a second down to a measly 80 gigabits a second, which is then passed on, obviously, to the level 2 and level 3 triggers. Once this data has been filtered, it's then passed on to the CERN data center, what we call the Tier 1 data center, which is located on the CERN site and is part of the visits tour if you sign up for one of the visits. Here we've got around, we process around 1 petabyte of data per day, and we've got around 150,000 processor cores located on the site. There's about 650 petabytes of disk, and then there's a further 690 petabytes of tape storage in the basement of the computer center as well. This sounds like quite a lot of processing power, but it's not nearly enough. In fact, it's a tiny fraction of the processing power that we need. So one of the other things that we did at CERN was develop the worldwide LHC computing grid. This is the largest computing grid in the world. We have so we have around 1.4 million computer cores with a storage capacity of 1.5 exabytes of data. It's located in around 170 sites across the world in 42 different countries, and this provides near real-time access to the 12,000 particle physicists who access the LHC data, who are doing the studies and the analysis of LHC data. There's around 2 million jobs running on the WLCG at any particular time, and we have a data transfer rate of around 260 gigabits a second. We've well rehearsed this when you can see.
Let's go to the future. So the numbers that Derek told you are impressive, aren't they? I mean, now we're used to cloud computing and those big hyperscalers, but you should think that the grid is something that exists for quite some time. It was actually instrumental to finding of the Higgs. We wouldn't have observed the Higgs bosons without the grid and without the impressive computing infrastructure we have here at CERN and spread out around the world. Now, there is another number that is important that Derek told you. I'm not sure you paid attention. You remember how many collisions we expect every time a bunch of particle crosses? Yes, you're paying attention. That's great. So the next generation accelerators and detectors expect to see at least 10 times as much. So if you looked at if you remember this nice picture, this nice animation that shows how then the particles spread out across the detectors, and you saw all of the different trajectories that need to be reconstructed starting from thousands and thousands of sensors and electronics output, digital output. You can imagine that when the original number of collisions becomes 10 times larger, you're going to need orders of magnitudes more sensors, and you're going to need orders of magnitude more computer powers to do that. So we already know that the current approach, if we were just to continue and hope in the evolution of technology to give us more power, would not be enough, well, especially if we correlate it to budget, right? So this would not be enough to actually solve the problems of the next generation's accelerators. It's been already quite a few years that the community has started to looking into alternative ways of processing, okay? And Derek showed to you, for example, the great approach that LHCb is testing, GPU farms for real-time selections, but studies of deep learning and AI algorithms, those kind of things are being introduced now in the detectors in order to find more efficient ways to actually do that. Now, obviously, I'm here because quantum computing is also one of these things we are looking into to understand whether it is a solution in the coming, I would say, 10 years as something that we could use for physics. Now, before talking to you about computing, I just wanted 1 second to go back to those initial concepts that are so famous about quantum computing and that are just needed to understand what I'm going to say in the future. So we already spent quite a few words on entanglement. You know more or less what it is. Actually, you knew it already before. Let me just ask if you know about superpositions and tunneling. Those are also things that are important for computing. Superpositions, what does it mean? Who can answer? No, you already answered before. Anybody else? Yes? Yes, like Schrödinger cat. So let's not go and open the box. So I prefer to think that it's alive. So this idea is that a quantum state can actually be in a superposition of many states. So if your classical bit is something that can hold either the 0 or 1 information, a quantum bit would hold the 2 at the same time. And you can think of it a little bit as looking at this, thinking about a coin that's spinning. While the coin is spinning, you can't see one face or the other, or rather, you see both of them kind of overlapping. That's really the superposition state of a quantum state. The only moment in which you can see either one face or the other is when you just stop it and take it and look at one face or the other. That's the measurement step. When you do that to a quantum state, the quantum state collapses into one of those options, and then that's what you measure. Okay, so this is as far as superposition is concerned. What about tunneling? Who can talk about tunneling? Anybody? I'm sure you all know tunneling. Have you ever been up in the mountains, walking, doing, randonnée, hiking? No? Okay, this is really a computer scientist conference. Come on. So tunneling, you are walking up, yes.
You've got 2 different energy states.
Yes. Exactly.
Tunneling allows you to go from one to the other without having to go over that barrier.
That's perfect. So if you are going up in the mountains, I'm sure you all felt like, oh, whether there were a tunnel that I could just cross over instead of having to walk all the way down and then going down the valley the other way. Come on. It happened to me many, many times. Anyway, this is something that happens to quantum states, and it's one of the main important reasons for looking into some specific technologies, for example, quantum annealers, okay? So those are basic, there are many more, but those are basic concepts about quantum states and quantum mechanics that can be used for computing. How? So let's think now a little bit in terms of computer science, and I'm sure I'm a physicist. I'm sure you can do that better than me. So if you think about superposition, what does it mean? I said I have 1 bit of classical bit, and this can hold, let's talk in big numbers. I have n bits in my memory. I can hold n bits of information classically. But if I have n qubits, then I can hold 2 to the n bits of information in there, okay? So I'm exponentially increasing the size of the quantity of information that I can store. Now, does it mean that I can process all this this information in parallel, does superposition actually lead to parallelism, to this big exponential increase in the number of operations I can run at the same time? This is a major question that needs to be answered. In theory, the answer is yes. In practice, we need to be careful with what happens when we retrieve information out those qubits. And this is why I stress the issue about measuring, about stopping your spinning coins. Then there is a question about how you use entanglement. Well, we talked about correlation, so entanglement is a very powerful feature that maybe can help us better representing correlations that are harder to represent classically. Now, to which extent this is true is also something that is debated and needs to be understood. What is the expense of actually building entangled states in order to represent these nonlinear correlations, okay? Are we able to build states that we actually could not simulate or in some sense also reproduce classically? That's the real question. Reversible computer. This is something that is more connected. Maybe if there are physicists in the room, they can answer better. Why am I talking about reversible computers? When you do quantum computing, you initialize your quantum state. Your operations are transformations of your quantum states somehow. And when you do them, by definition, they are reversible. Those are called unitary matrices that represent your operations. It's that detail at the moment. But the bottom line is that in principle, whatever algorithm is reversible. This is interesting. As you know, there is the concept of reversible computing. Again, we need to be careful with what happened when you actually measure this state. And then stochastic. You know there is a paradigm of stochastic computing. It's a way of extracting and manipulating information that takes into account the fact that there is some sort of statistical uncertainties that related to your results. Well, this is indeed the case also for anything that is the output of a quantum computation. And again, the reason is related to the fact that we are measuring a quantum state. And this is a probabilistic phenomenon. And then to this is connected the questions about stability and reproducibility. If I have an algorithm that will give me a certain output with a certain probability, how reproducible is that output? How stable is the result? After all, the states that hold my information, but also the operations that I apply to them are quantum transformations, are quantum states and quantum transformations. So they do not live in a world in the same way classical transformation do. Quantum states stay coherent only for a certain amount of time. After that, I can't know, I need to measure. Okay, so there are all of those questions that actually make the field of quantum computing far from trivial, but also extremely, extremely interesting. So, that said, there are a lot of very practical problems that you can try to solve with these algorithms. And we've done so as CERN community, but also more broadly speaking, as high energy physics community. Already for a few years, there has been a lot of interest in trying to design algorithms, for example, to simulate physics in a more efficient way, okay? At the moment, one of the biggest problems in the whole computing resources, I would say, problem for the future detectors is related to simulation, mostly detector, not first principle simulations, but still, it's a big issue. And in fact, generative models, classical generative models are on the hype now for that. But from the quantum perspective, we can think of using quantum computers as a natural simulation for some physics processes, because at the end of the day, the production mechanisms of the particles that we see in our accelerator is quantum, okay? So there are many applications that are already looking into that. You can think of using quantum computers also to do pattern recognition. And the reason there are many reasons, but among the things that I listed before, maybe you can think about tunneling as one of the reasons for that. You can think about superpositions as one of the reasons for that. Quantum computer is going to be able to hold in a compact state a lot of those points in your detectors, and then maybe very fast you can optimize your problem. You can find the optimal solution and the optimal pattern that's actually describing your the data that you see. Okay, so this is another very, very practical application that already exists. I keep going back to artificial intelligence and deep learning and AI. That's really my first love, if I can say that. So I'm happy to say that this is also one of the fields that in which quantum computing can do something. Maybe not today, in the sense that one of the main things for scalable and real practical applications of AI, of course, is large data sets. So everything that's highly dimensional. That's not the easiest way to use quantum computers today. Mostly for, because the technology still has to get there. But one of the things we were able to do, you saw all of the nice animations and explanations that Derek gave you on the accelerator complex. Beside accelerators that are used daily for producing particles for the experiments, there are also a lot of other more experimental beamlines, so infrastructure that is used to understand how to improve the technology for the future. So we worked with some colleagues from the accelerators department that to the problem of trying to automatize at best the tuning of a beam of particle within an accelerator. You saw the animations with all of these different steps that actually accelerate one after the other the particles to a certain energy or to a certain trajectory, okay, in the accelerator. So this is, if you want, is a multi-step optimization problem, okay? We try to solve that with a reinforcement learning approach that we implemented on the quantum computers. And the great thing is that we found out that we could accelerate the training of those classical agents by using quantum computers. So we could train agents that are much smaller and that need a very small amount of data to actually get to the optimal solution. And this might not be a problem, I just want to point this out, might not be so important for the typical classical machine learning problem when you can, you have NLPs, you train them over the whole internet of data or whatever. But for some cases, and particularly for reinforcement learning applications, you often have the problem of building labs and experiments to gather the data that you need to train your agents. And this sometimes is the bottleneck to the solution. The fact that you can actually train something that is efficient by using a very, very tiny amount of information is really important. The other thing, this is not, let me point out, this was actually applied to the existing beamline. It was not a study that was done in a completely simulated environment. Okay, we actually used this quantum computing trained agent on the awake experiment at CERN. So I would say I gave you some examples of the things you can do today. What if we could actually move one step forward? After all, today all of the realistic applications of quantum computing have been focused on processing classical data. I have data of some kind, I need to find a way to load it on my quantum states, and then I process it through quantum computers. What if I were in a situation in which I had access directly to quantum data that I don't measure, and that I can process directly through a quantum algorithm? That would be the very, very, I would say, big change in the use of this kind of applications. And it's not science fiction. I mean, it is science fiction maybe today still, but there are people that are looking into that. I mentioned briefly before the aspect of quantum sensing, so developing sensors that are based on quantum mechanics phenomena in order to do, I don't know, detection of a specific particle or a specific problem. So these researchers could actually leverage quantum algorithms applied directly to their sensors, okay? This is just something that might come in the future. And I think we can go back to what we have today.
Thank you. Yeah, so CERN's fundamental role as an organization is to provide infrastructure for particle physics research to take place. So we provide all the infrastructure. This is a photograph of the accelerator control room, of the LHC control room. And you can see IT technologies form the core principle of all the work that's being done at CERN. particularly for the control systems. You can see all these fixed displays, plus all the monitors around the room, which the operators use to control the accelerator. So IT plays a very key role in all of the work that we do. And in fact, Java has also played a pretty key role in a lot of the software that's developed, both in terms of for the control systems and also in terms of things like business computing. All of that's done using Java technology as well. Beyond that, of course, we also have mechanical engineers, as I say, as an organization providing infrastructure. That means we also have mechanical workshops where we will actually design, simulate, build, and then fabricate and actually install pieces of equipment working in extreme environments. In fact, one of the first places that was created at CERN was a mechanical workshop where we actually built the different components of the accelerator. The accelerators themselves are an extreme environment for mechanical systems working at cryogenic temperatures and high radiation environments, and so it requires very specialist materials, specialist equipment, and also very smart people to actually build these mechanical systems to work in these extreme environments. We even have our own fabrication facility. We have things like multi-access CNC milling machines with capacities around 40-ton items to build these specialist components which operate within the LHC and other accelerators. And all of these are designed and built and fabricated actually on site at CERN. Beyond mechanical engineering, of course, we also work on specialist materials. Mechanical engineers themselves work with special materials. We're one of the few places that actually build items out of materials such as niobium, for example, in order to, for operating within the accelerator complex. We also have material scientists who are developing different materials to be part of the detectors. This particular guy, he's looking at some crystals of lead tungstenate. This is a crystal which is 86% by weight metal, but it's completely transparent. And there's around 76,000 of these crystals inside the CMS detector. As well as, of course, the technologies developed at CERN, there's also spin-off technologies. So we have, for example, the technologies, small particle accelerators have been redeployed and used for things like proton therapy, which is a type of radiation therapy which allows very precise application of radiation therapy, which causes minimal damage to the tissues around about the tumors. And this was a technology which was developed directly using the studies that were done at CERN. Beyond that, of course, we have things like the detector technology has been reapplied for example, in ports and harbors where we can use the same detector technology to look inside trucks and other vehicles without unpacking them to speed the movement of particular materials around the world. CERN is also home for UNOSAT, so this is the UN agency for satellite image processing. Where we will take satellite images and then use the computing infrastructure available at CERN to be able to study these satellite images for humanitarian purposes. For example, this is a satellite photograph of before and after of the earthquake in Nepal. And by using image processing, we can actually detect and measure the impact and the impact of the earthquake, and also help coordinate response teams in these kind of humanitarian disasters around the world. More of an anecdote than anything else, because of the very precise nature of the particle accelerators we have at CERN, we can actually even detect earthquakes themselves. This is actually a plot of effectively what it was is the position of the particle beam within the LHC. And you can see that there was an earthquake, and we can see the impact of that earthquake on the position of the beam within the LHC. What's interesting is this earthquake actually took place in New Zealand, and we detected it at CERN. Gives you an idea of precision of this particular device. Beyond that, of course, there's more. We have the antimatter factory. This is a real building that we have at CERN where we actually make antimatter every day. You probably saw announced in the news relatively recently about the research that was done on the effect of gravity on antimatter, and the effect it largely affects antimatter much in the same way as it affects matter. We have the Isolde. This is a facility which actually makes specialist isotopes for nuclear medicine. And we also have the cloud experiment. So the cloud experiment is climate scientists are actually using particle accelerators, the particle beams, to simulate the effect of cosmic rays and studying how the effects of cosmic rays are affecting cloud formation. the Intergovernmental Panel on Climate Change say that one of the biggest variables in climate models today is trying to understand how cloudy was it in pre-industrial times. And this is one of the few experiments in the world which is actually studying this particular area and helping us refine the different climate models in order to obviously better understand the impact of humans on the climate. Latest findings from the cloud experiment have helped to explain the mechanism for the increase in accelerated rates of loss of sea ice in polar regions, while simultaneously reducing temperatures in lower latitudes. And of course, we shouldn't forget the alpha magnetic spectrometer. This is a particle detector which is actually attached to the International Space Station, but this device was constructed at CERN and is used for studies around things like dark matter, dark energy, antimatter experiments, and the fact that it's outside the Earth's atmosphere allows us to also have very precise measurements of cosmic rays.
I think we're a little bit beyond schedule with these slides, really, because we are getting closer to the coffee break. I just wanted to show you an example of how you actually use the sensors. Very briefly, so Derek introduced to you to a lot of different things that are happening at CERN beyond experiments. A lot of questions you can answer with by measuring very tiny signal, very small amount of energies. You don't always need to go all the way to a collision, to an LHC collision. This is the case for a lot of experiments that are looking into dark matter, for example, or gravitational waves. So for those kind of experiments where you need detectors that are sensitive to tiny changes in their setup, then quantum sensors are probably among the most important or very promising techniques that can be used. And so there are people that are looking into sensors based on atoms, single atoms technology, or photons-based technologies, and many more. Okay, so I kept it short for your sake.
So, CERN, place of contrast. The largest of machines in the world are used to study the tiniest of particles. It's an organization fundamentally based on technology. Technology organization from all the different systems that we're developing, pushing the bounds of technology, creating new technologies and in extreme environments, and allowing us to develop things which ultimately are the benefit for everyone. And it's fundamentally the purpose of CERN is providing an infrastructure and an organization which can develop technology to allow particle physics to take place, of course, but also share these developments with the rest of you. Everyone in the world has got free access to the technologies that are developed at CERN, and we can share them globally. It's an open organization. As you can see, it's an organization which we are welcoming people to come and visit, see what's going on. I'd also encourage you, there are many people in the audience actually who work at CERN, so if you see anyone with one of these badges, feel free to speak to them. And for those people who work at CERN, I'm sorry, there is no such thing as a free lunch. And in the summary, I think there was a nice statement on, if you remember a long time ago, there was various people come to visit CERN, and one of the visitors we had actually was Tom Hanks, and he concluded quite nicely actually some of the work that's done at CERN when he said that magic is not happening at CERN, magic is being explained at CERN. So with that, we'd like to close. Thank you very much, both from Sofia and I, for your attention. It's an amazing place working at CERN. I hope you profit from being here. Take the opportunity also tomorrow to visit the exhibitions as well. There's lots going on there, as well as, of course, all the fantastic talks that are happening here. Well, happy to speak to you later as well over coffee.
Thank you.
Thank you.
Welcome to CERN.